Hello, everyone. Welcome to the Multi-Agent Learning Seminar. It is my pleasure to introduce our speaker today, Naveen Raman. Naveen is a second year PhD student in the machine learning department at CMU, where he's advised by Fan. His research focuses on improving decision making in uncertain environments, particularly in areas like multi-agent learning, bandit feedback, and sequential resource allocation. And his work has real-world applications in fields such as food sustainability and healthcare. Naveen is also a recipient of the NSF GRFP, and he'll be presenting today his work on global rewards in restless multi-armed bandits. So over to you, Naveen.
That sounds great. Thank you. So today I'll be presenting my work on, as was just said, global rewards and restless multi-armed bandits. And so let me share my screen. And so I think this work or this kind of presentation will be in two parts. The first part will talk a lot about kind of some of the theory and algorithms underlying kind of restless bandits and how we extend it to a particular scenario. And the second part will describe why we did this and kind of a real world case study in a domain called food rescue and how we can kind of bridge the theory practice gap in kind of food rescue by applying these techniques. And feel free to ask questions kind of throughout or whenever works best for you guys. So I'll start right now. And I assume you guys can all hear me. Is that correct? Okay, sounds good. And so to motivate the problem, I'm going to start with kind of a quote from the United Nations on food insecurity. And so there's a quote saying that enough food is produced today to feed everyone on the planet, but yet hunger is on the rise in some parts of the world, and some 821 million people are still considered to be chronically undernourished. What does this mean? This means that we produce enough right now to feed everybody, but yet despite that, we have kind of a distribution problem. There's enough food out there for everyone. We need to find a way to get it to the people who actually need it. And so this is where kind of food rescue applications come in. And I'll describe what they are at a high level and then go through a quick video demonstration of this. And so what food rescue organizations are these kind of nonprofit-led organizations which take food from places that have a lot of them, like grocery stores, restaurants, and deliver them to places that really need it, like food banks, shelters, and places like that. And they do so through volunteers. Essentially, you can download an app in kind of many major cities. And what the app will tell you is it'll say, hey, look, there's a new kind of trip available from, say, a grocery store nearby to a food pantry or food shelter nearby. Can you help do this? And so you can actually do this yourself. I've done this myself a few times. And you can actually just go to the kind of pickup location, pick up the food in your car, bike, walk, or whatnot, and just bring it over to the kind of donated location. And this saves, I think, millions of pounds of food a year, at least in Pittsburgh. And I know nationally there's many other kind of organizations. And in particular, this work is done in coordination with a group known as 412 Food Rescue, which is a kind of local food bank or local food kind of rescue organization in Pittsburgh. And they run lots of different rescue trips, and we kind of work with them throughout this project and many other projects. And I'll give kind of another demonstration of what food rescue is through a video made by 412 themselves.
Did you know that globally, we waste up to 40% of our food? Perfectly good food. If we could recover all of that food, we would feed all who are food insecure 4 times over. So how can you help? You can be a food rescue hero. It's easy. Download our app and sign up. Food rescue matches excess food to agencies in need. You get push notifications so you can help transport the food. You can rescue food when you're on the way to the store. Help deliver healthy food to those in need on your way back from the gym. Anywhere and everywhere you go, there's a chance to pitch in. Just find the rescue that fits you, claim it, and deliver. In as little as half an hour, door to door, you can help end hunger. Do you have the drive to change the world? Join the movement of food rescue heroes. Download the app today.
And so I'll go through a quick walkthrough of how this actually works in practice. And so the first kind of step is trip notifications. Basically, everyone who has the app download will get some notification based on kind of their location preferences and whatnot for the fact that there's a new trip arriving, say, from downtown to somewhere nearby. And then based on that, the kind of volunteers themselves can look at these trips and say, hey, look, is this something that I want to complete? Is this something that's nearby and maybe is kind of feasible for me to actually complete in practice? And if so, you can say, hey, look, I want to accept this and actually start the trip. And once you do that, you'll actually go to the kind of physical drop-off or pickup location, pick up all the food and actually bring it to the drop-off. And so this is largely volunteer-driven. The kind of key, I guess, lever element that the food rescue platform has to control notification or to control kind of trips is their notifications. And basically the kind of fundamental question is, who do you notify for which trips? And there's this kind of delicate balance there. If you notify people too many times, they'll start to get burned out, they'll get bored and kind of leave the system. But if you don't notify people enough, then what'll happen is that some of the food that you want to get donated will go wasted. And so the kind of question that we ask is how can we notify volunteers in this kind of food rescue setting to make sure that we maximize the amount of donated food while also keeping the volunteers engaged? This question kind of came out of previous real world kind of studies, real world kind of RCTs, where we found that we can develop good algorithms to maximize the amount of donated food. But what will happen is that over time, the number of volunteers diminishes, or the number of volunteers who are engaged diminishes. And so the question is, how do we also incorporate that in so that the food rescue platform maintains a kind of healthy volunteer base while also making sure that we maximize the amount of food donated? What I'll go through next is a kind of stylized model of food rescue. And this is kind of give intuition for how we model the problem itself. And I'll describe how we can develop notification algorithms built on this. And so in the food rescue platform, you can imagine there's kind of two sides. On one side is the volunteers, and on the other side is the platform itself. Each volunteer has kind of two attributes that we'll talk about first, and then there's a couple other things we'll add on in addition to that. So each volunteer has both a state and an action. The state you can imagine is being either engaged or not engaged, and the action being notified or not notified. And so for each kind of new trip that arises, we have to determine which subset of volunteers will we notify and how will this kind of impact whether or not they're engaged. In addition to this, each volunteer has a match probability, little p, and a transition probability, big P. The match probability basically says, if I notify this volunteer, what is the probability that they actually say yes and they actually kind of complete the trip? The transition probability says, if I'm engaged or not engaged, if I'm in some state, and I get some notification or don't get a notification, some action, then what kind of state will I be in the future? Basically, how does my engagement change over time based on whether or not I'm notified? And right now we assume that the kind of states and actions are binary, but in kind of future slides, we'll show that we can expand the state space and we can deal with kind of more nuanced definitions of engagement. And so on the platform side, what we have is kind of a complementary aspect. We have the set of states for all volunteers, which we call bold S, and the set of actions for all volunteers. And basically a set of actions says which volunteers do we notify, where there's kind of n volunteers in total. In addition to this, we have two other components. The first is a reward function. And basically what the reward refers to is the probability that any volunteer matches. If I assume that each volunteer has some probability of matching PI, then basically this says, what is the probability that if I notify each of these volunteers, that at least one of them will pick up and say, yes, I'm actually going to pick up this trip. And so we can imagine that that's our kind of reward corresponding to the trip completion rate or the match rate. The other component that the platform has is some kind of budget constraint. And basically this is for logistical reasons and says we can notify at most K volunteers at a time. You can view this kind of logistical constraint in one of two ways. One is just saying we don't want to notify too many volunteers at one time, and so we'll kind of naturally impose a budget constraint K. The other is that in some situations, when not enough volunteers say yes to a trip, food rescue platforms themselves will manually call up volunteers and ask, do you want to go on this trip? When food rescue platforms do this, there's this kind of natural limit on how many people they can call in a given hour or a given minute. And so K kind of represents logistical or physical constraints on how many people can be actually notified or called by these kind of food rescue platform dispatchers or people who actually do the organization. And so within this, the problem we're trying to look at is how do we optimize the notifications or the actions taken to maximize both the engagement and the trip completion rate. Formally, we can represent this as some kind of problem where we're trying to find a policy pi, which basically says, given a state the volunteers are in, which volunteers do I notify or what actions do I play? And we want to maximize the kind of discounted reward with two components. The first component looks at kind of the trip completion rate or the probability for a given trip that volunteers actually match. The second looks at the engagement rate, basically what fraction of the volunteers are actually engaged in this kind of given time step. More generally, we can think about the problem as basically saying we have two components. The first is some kind of global reward. And here, global reward basically means that it's a reward that we can't factor into some kind of sum over the volunteers or the arms. And the second is some kind of separable, kind of nice linear reward. And so the question is basically, how can we select a policy that accounts for the fact that volunteers or arms change state over time while maximizing both the global reward and this kind of local linear reward? And so I'm going to pause here and see if there are any questions on the setup. If not, I can keep going into kind of more details on approaches to this and how we actually tackle this problem.
I have a question. I don't know how to raise my hand. Is it?
Yeah, go ahead. Uh-huh.
It's in reactions. So there. Are you just going to maximize these two types of reward functions equally, or are you gonna experiment with, weighting the global reward function more than kind of this linear combination of individual reward functions?
For this talk, we weight them equally, but in the actual paper, we have kind of experiments where we change around the weighting and we try out really weighting the global reward or the actual engagement. We do so right now just for simplicity, just to kind of simplify the presentation, but in practice, we agree that probably the global reward or the kind of match probability matters much more. You could also imagine that we just change the scale of the global reward to account for the fact that we want to upweight it that much more than the kind of engagement component.
Yeah, thanks.
I think another person has their hand raised.
Yeah, I was wondering, if you can walk through again what you are optimizing globally and what you are optimizing locally. I think I was not very clear on the transition from the food rescue optimization to the generalized problem.
Yeah, that sounds good. So basically what we're trying to optimize is two components. In the food rescue scenario, we have both the trip completion rate, which is the kind of term on the left, and the total engagement rate, which is the term on the right. And you basically want to abstract this out and say we have two components. One is kind of non-linear in some sense, and the other is linear. Basically, as I'll go over in a minute, a lot of prior work can solve this problem when all the rewards are linear, or basically you can sum them over the individual arms or volunteers. But here, the kind of trip completion rate is non-linear. And the reason I'll explain in a minute is basically because if I have two volunteers, each of them with 50% match probability, notifying both of them does not give me 100% match probability, but instead gives me kind of 75% match probability instead. And so we're trying to think of the problem of basically, okay, let's take that first kind of objective function, the trip completion rate, and let's try to generalize this to say, this is some kind of nonlinear reward function that we have. And then we also have some linear component, and how do we maximize the kind of sum of the two together?
What is the linear component? Is the engagement of
exactly, yep.
Okay, thank you.
You could also imagine we just have some kind of nonlinear reward function we want to optimize for, and both are kind of equivalent views of the same thing. And so one kind of natural way to solve this is through restless bandits, and I'll explain what that is in a minute. And essentially, what restless bandits are essentially a model of decision making that lie kind of midway between multi-armed bandits and reinforcement learning. Typical multi-armed bandits, how they work is you have a bunch of arms, you pull arms that give you some reward, and you try to learn over time which arms are the best. In kind of restless bandit, the challenge here is that each arm is kind of a marked out decision process. You might know the MDP fully, like you might know how the states and transitions and actions and rewards all play out. But the challenge is that each arm kind of evolves based on whether or not you play an arm. And so you can see it's kind of multi-armed bandits with an additional state added on top, bringing it closer to reinforcement learning. And a lot of the work in kind of traditional restless bandits, what they do, as I'll describe in a later slide, is they determine kind of which are the top arms to pull. And they rely on an assumption that the reward that you have for kind of pulling arms 1, 2, and 3 is the linear sum of the reward for each arm individually. Basically, we can treat the reward function as kind of a linear sum over the reward for each arm individually. In our setting, what we're trying to investigate is kind of inter-arm relationships. Basically, my reward is not so nice. It's not just separable. And what do I do in that situation? What do I do if my reward is actually global, where pulling arm 1, 2, and 3 cannot just be separated into a sum of pulling arm 1 plus arm 2 plus arm 3? And in that case, what does this imply for kind of the optimal policies? And so that's the kind of setting we're looking at, trying to see how do we take the traditional restless bandit setting, where the rewards are nice and separable, to a kind of global reward setting where the rewards are much more kind of complex with inter-volunteer, inter-arm kind of relationships. And so the key question is, how do we optimize the restless bandit problem with global reward? And that's what we'll kind of go into next. And we make one key assumption here, which makes our problem actually kind of tractable. And we assume that the kind of global reward we're dealing with is a submodular monotonic function. What submodular monotonic functions refer to is the idea that a reward is submodular. And so as I pull more arms or as I notify more volunteers, my reward is diminishing. You could imagine that if I've notified 10 volunteers, the 11th volunteer I notify is more valuable than if I've notified 100 volunteers and the 101st volunteer I notify. And so as I notify more volunteers, it becomes less and less valuable for me to notify extra volunteers. And the reason for this is kind of the example I mentioned before. Basically, if I have 2 volunteers, each with kind of probability 50% of matching, then if I notify both of them, the chance that either one of them matches is 75% rather than 100%. And this is because the maximum kind of trip completion rate or match probability is 100%. And so as I add more and more volunteers, I'll get closer and closer to 100% without necessarily ever getting there totally. And so modular monotonic functions basically refer to the idea that we have this reward where adding on or notifying extra volunteers helps, but in kind of a diminishing way over time. And the reason we pick this is because it nicely models our problem, but also is kind of a general class of reward functions that are easy to optimize, at least approximately, and you can see them in all kinds of applications. And so to recall our goal, what we're trying to look at is the food rescue optimization problem. Basically, we have both the trip completion rate on the left and the kind of total engagement on the right, and we want to maximize these through some policy pi. And more generally, we want to look at the problem of how do we maximize kind of a global reward, which is nonlinear, non-separable, and a kind of local or linear reward that is separable. And so to do this, let's first look at what solutions look like if we ignore the global reward, basically looking at only the restless bandit scenario. And so to do this, I'm going to introduce what's called Whittle indices. And essentially the way that standard restless bandits work is they say we have these kind of a bunch of arms, and I can pull at most k of them. How do I optimize this? I'm going to give each arm some kind of index or some kind of value, and then say these are the top k arms. These are the ones that I want to pull, and I'm basically going to rank the arms best to worst and just go down, go down the list and pull the top k. The question then is, how do you actually rank this? How do you actually determine how good an arm is? And this is where the Whittle index comes in. And the kind of key question there is, it's basically asking, okay, if I apply some kind of penalty to pulling an arm, how large does the penalty have to be so that you're indifferent between pulling the arm and not pulling the arm? And so you can imagine that each arm might kind of have a Q value for it. And if I have some penalty W for pulling the arm, in this kind of equation at the bottom, you can see I have a penalty negative WAI. Basically, if I have a penalty W for pulling the arm, then what is my kind of Q value? And you can think that if arms have larger Whittle indices, what that means is I need a larger penalty to disincentivize me from pulling an arm. Or in other words, it's more valuable to pull the arm. And so what we look at is basically saying, what is the penalty we need so that you're not going to pull the arm anymore? So that pulling and not pulling are basically the same, or basically when not pulling kind of gets ahead of pulling, what is the smallest kind of penalty for this? And you can just imagine it as basically saying we have some kind of value for each arm, and you rank the arms using this. The challenge with using this kind of directly for our problem is the kind of separability issue. The rewards in our scenario are global, non-separable, or non-linear. But in this kind of formulation, you can see that we generate Whittle indices for each arm and are realizing the assumption that we have kind of an independent reward for each arm. And so we can't just directly apply it because there's kind of contrast in how the reward function is structured. Another kind of natural solution to this is using reinforcement learning or even deep reinforcement learning. And this is something we tried out ourselves and found that this didn't work so well. And the reason being that the state and action space sizes are very large. And so even approximately finding this is kind of difficult is what we found. And we'll show this empirically using kind of deep Q networks, and we'll show that this doesn't really work so well. And we tried out a few different things there, and it doesn't really scale that well with large number of arms. And so the way we tackle this instead is through 2 new main methods that we do called Linear and Shapley-Whittle. And basically the key idea is we can take the old kind of Whittle index idea and just apply it to a modified version of our problem where we take the global reward and linearize it in some way so that it becomes a standard restless bandit, where the global reward is transformed into some kind of separable reward function. And how Linear and Shapley-Whittle differ is how they actually kind of linearize this global reward and how we actually deal with that. And so I'll go into that. And so basically we'll go into 2 different ways of decomposing our global reward into a linear sum. The first is called a linear Whittle index, and it's kind of the most baseline or most basic version. And basically what it does, it says, if I have a global reward pulling arm 1, 2, and 3, then I can approximate this as basically saying, I pull arm 1, what is the reward I get for pulling only arm 1? I pull arm 2, what is the reward I get for pulling only arm 2? And I pull arm 3. What is the reward I get for pulling only arm 3? And so that's the kind of idea there, is that we can basically approximate our kind of linear sum into this kind of decomposed reward for each arm. And this is kind of an approximation or a linearization of our global reward. The second way we look at this is through what are called Shapley values. And basically what Shapley values are is a way to do kind of credit assignment in a group. If I have a group of 3 people, then the way I want to determine what the value of each person is by basically saying, okay, if I take person 1 or agent 1, then what is the average kind of marginal contribution? And I look at how much does the reward increase when I add 1 to a group with, like what is the difference between having a group of 1 and 2 versus just 1? Then I look at what is the difference between having a grouping of 1, 2, and 3 versus just 2 and 3. And this gives me a sense for the value of each arm. You can apply a similar value here where you basically say, let me pre-compute the Shapley value for each arm and say if I pull out arms 1, 2, and 3, then the approximate kind of global reward is the kind of Shapley value for arm 1 plus that of 2 plus that of 3. And so basically linear and Shapley-Whittle, what they represent is 2 different ways of linearizing our global reward, which allows us to use a kind of Whittle index policy from before to rank arms and pull them. Yes.
So do you calculate these Shapley values for just like say smaller numbers, or because I hear the Shapley value calculation is a expensive computation. So how many like arms are your limit when you come to calculating the Shapley-Whittle index?
That's a good question. So exact Shapley value calculation is, I think, exponential probably, or very expensive. So what we do is we just approximate it. We get samples and we say, because the Shapley value is bounded and we can get like a few samples or not too many samples and it'll converge fairly fast. And we can just approximate Shapley values in this way and it works fairly well in practice.
Okay, thanks.
Any other questions? All right, that sounds good. And so I'll go through some quick kind of synthetic empirical evaluation, describe a few extensions, and then I'll go into kind of the details of a case study involving food rescue. And so synthetically, what we can basically do is we can use the reward function from before, basically that kind of trip completion probability or whatnot, and generate synthetic data and basically show that our linear and Shapley policies do well, and they do especially well as kind of the number of arms increases, and we can do much better than kind of greedy policies or kind of other baselines. And we can also see that Shapley-Whittle does better than linear-Whittle, kind of justifying the reason that we actually generate kind of Shapley-Whittle policies. But one kind of issue that they might run into is that when the reward is very, very kind of nonlinear, the problem might kind of break down. And I'll explain this through an example of why we need kind of adaptivity to the amount of nonlinearity or kind of globalness in the actual reward. And so basically the issue is that linear and Shapley-Whittle can perform very poorly in some scenarios. And I'll explain a scenario like this first. So basically imagine that we have a scenario with a bunch of arms and a very high budget. And in this scenario, you can imagine that if I have kind of all arms initially in state 1, and then once you pull an arm, it goes to state 0. If I pull an arm that's in state 1, I get, no matter what, if I pull any arms that are in state 1, I get a total reward of 1. And if I pull no arms that are in state 1, then I get a total reward of 0. Basically, the key idea is that the way the optimal policy should work in this scenario is basically say, hey, look, if I pull more than one arm, I don't really get any more reward than pulling only one arm. And so what the optimal policy should do is just pull arms one by one. So in time step 1, pulls arm 1. In time step 2, it pulls arm 2, so on and so forth. And this will give me a reward of k. The issue with the kind of linear and Shapley-Whittle index and kind of any index-based policy is that it'll rank the arms and it'll say all the arms are equally good. All the arms will give you positive reward. And it'll pull all the arms at once in the first time step, and that'll give you a reward of 1 instead of a reward of k. And so basically the issue is that instead of determining or kind of recomputing the indices one by one for each arm, it'll compute them all at once and basically say they're all equal and let's pull all the arms. And this can lead to kind of bad situations where we get kind of poor approximation ratios. And so I'll quickly go through 2 ways that we actually kind of get around this, 2 new forms of getting around adaptivity. And I'll show how this does in kind of practice using actual kind of synthetic experiments. And then I'll go into a food rescue data set for that. And so basically what we do is we have 2 new forms of additivity or 2 new algorithms that add on top of the linear and Shapley-Whittle indices. The first is called iterative linear Whittle. And basically what that does is it says, before we computed or pre-computed the linear whittle index for each arm, and we pulled the top k. In this scenario, what we say is, hey, look, we're going to compute the whittle indices, pretend we pulled the first or the best arm, and then recompute the whittle indices basically based on what is a new kind of reward. And the reason we can recompute this is because we know that no matter what, let's say I pull arm 2 first, then I can recompute the reward I would get for pulling arm 1, given that I already pulled arm 2. And so basically this allows me to kind of get a more fine-grained version of what the reward is and iteratively pull these arms over time. And this would solve the kind of problem seen before, where basically we one by one pull arms, and this can avoid the issue of all the arms being pulled at once when it shouldn't be. The second kind of way we go about this is using Monte-Carlo Tree Search. And I'm not going to go into the details here, but essentially the key idea is that we search through combinations of arms. And for each combination, we say, what is the kind of reward for this combination of arms? And let's use the kind of current reward at the current time step and a prediction of the future reward to predict or compute the linear whittle index. And the kind of key advantage this has over, say, just standard linear whittle index is that we can search through different combinations of arms and exactly compute the reward in this time step. And of course, there's analogous definitions for Shapley-Whittle as well. And there's more kind of in-depth descriptions, discussions, or whatnot of these methods in the paper itself. So I'll refer to that. But essentially, the key idea is that we can add kind of searching or adaptivity methods on top of these linear Whittle and Shapley-Whittle policies that allow them to do better. And we show that they can do better through evaluation on synthetic data. Basically, what we come up with is different types of reward functions. So we can come up with a linear reward or kind of the probability-based reward mentioned before, and a couple other reward functions. And what we basically show is that our policies, these kind of Shapley-based policies, and especially kind of MCTS Shapley, the kind of orange one at the bottom, does really well across both the reward functions and when we change the number of arms. And so what we find is that in general, we find these kind of Shapley-based policies do really well. And moreover, we find these kind of reinforcement learning-based policies kind of fail to scale. And so as you increase the number of arms, they get worse and worse. And across these kind of settings, we find that using these kind of index-based policies that are modified for the global reward do fairly well. And we find that these kind of adaptive policies are especially important when the reward function is highly nonlinear. We compare how different policies do across reward linearity. Basically, we vary the amount of linearity in the reward, and we see how do different policies perform. And we find that across both the for different numbers of arms, what we find is that this kind of MCTS Shapley policy does fairly well and does better than kind of the alternatives. And we find that the kind of linear Whittle policy, which doesn't really account for the adaptivity as well, does the worst across both kind of settings. And so this kind of justifies the need for policies that do better than these kind of based on linear Whittle index and Shapley-Whittle index, and that account for the kind of reward linearity that's found in practice. And so I'll pause here and see if there are any questions on kind of our methods and how we apply them to kind of synthetic data.
I guess I'll just ask one quick clarifier. In terms of linear Whittle and Shapley-Whittle, I understand how you decompose the reward using a linear function or the Shapley value. How again is that implemented in influencing which arms are pulled? I guess it's through Whittle, which is the penalized version of the Q value for each arm, right? Or
exactly.
Am I misunderstanding that?
Basically, once we decompose a reward, you can imagine that each arm has its own kind of reward function. And once we do that, we can compute the Whittle index for each arm using kind of standard restless-multi algorithms and whatnot.
Which is the expected penalty to basically disincentivize that arm, right?
Exactly, yep.
Okay.
And then once we do that, we can kind of rank the arms in each state, and we can basically say these are the top K, and we'll pull those K.
Okay. How is that different than just estimating the expected value of each arm? Or is it essentially doing that because you need to learn the penalty to disincentivize it?
Yeah, they're very similar. I think if you estimate the actual expected reward, it's very similar to kind of this kind of penalty-based approach. The reason that people use the penalty-based approach in practice is because you can prove that using this kind of approach is kind of asymptotically optimal for the restless bandit. And so that's why a lot of the restless bandit literature uses this rather than the kind of expected reward-based approach. And I think there's kind of examples where you can show the expected reward-based approach might not work as well or might fail. But I think in general, you can use the kind of intuition that they're very similar.
Okay, thanks.
There's also another question, I think.
Oh, yeah. So I was just like, in terms of interpreting this graph you have here, like I was just looking at the range of the reward from like 1.0 to 1.8. Like, what is the full range? Is this like from 1 to 2? And what is a performance at 1.0? What does a performance of 1.0 mean compared to a performance of like 1.8?
That's a good question. And so the way we deal with this is we call this a normalized reward, and we normalize this by some kind of, we call it the random algorithm. Basically, we pull a random k subset of the arms. And so a reward of 1.0, or a normalized reward of 1.0 basically says you achieve the same amount as if we just ran a random algorithm. And so this is basically saying how much better are you than kind of the randomized algorithm. And so like a reward of 1.8 says you're 80% better than just playing a random kind of random arm. And so I think if you look back, I think in this one, when the number of arms is small, we can plot like what is the optimal policy, basically by just kind of brute forcing and computing the optimal policy itself. And that's a little dash red line at the top. And so what you can find is that in many kind of these situations, our policies are very close to optimal. And so that gives you a sense for like, okay, there's not really that much more room or much more you can add on top to what the policies are doing right now to reach the kind of optimal value. And that's the kind of intuition I would have.
Thank you.
Any other questions? That sounds good. If not, I'm going to move on to kind of an extended food rescue study. And then afterwards, I'll describe some couple quick takeaways, and then I can open the floor to questions again. And so we want to apply our data set, as kind of mentioned before, or our kind of models to help with notifications in this kind of domain or problem called food rescue. And so there's a few challenges in actually applying our model as is to the food rescue data set. The first of which is multiple timescales. And basically what that refers to is saying, hey, look, we have food rescue kind of applications occur on a trip-by-trip basis, but also volunteers might change state or might change engagement on a weekly basis. And I'll get into that more in a minute. And then another thing is trip context. Basically, the actual details of the trip impact the match probability. So rather than each volunteer saying, oh, I have a 1% chance of matching, it really depends. If the trip goes from downtown to somewhere near me, maybe I have a 50% chance, but anywhere else, I might have a 0% chance. And the last thing is actually defining engagement. How do we actually get the values for engagement in practice? And that's kind of another big challenge from a modeling perspective. And so I'll first talk about multiple timescales. And basically, food rescue operations occur in two different timescales. On the short timescale, you can imagine this happens multiple times a day. They need new volunteers for each kind of new rescue trip. But in the long timescale, you can imagine that volunteer engagement might change on maybe like a weekly basis. So it's not that, oh, every time I'm notified, my engagement changes, but rather it's the accumulation of notifications. Maybe if I get like 100 notifications in a week, I will become more disengaged or more engaged depending on how I act. And so we want to model both of these. And the question is, how do we actually model this in practice? How do we incorporate this into our model? And so the way we do this kind of at a technical level is we basically expand our state space. And so the state space basically says, hey, look, how many notifications have there been this week? And we'll kind of count this over time and we'll kind of accumulate, oh, there's some notifications they've been. And then we can also say, okay, it's been a week. Let me change the kind of state for each of the volunteers based on the total number of notifications that they've kind of accumulated, or the total number of times we've notified them. And this way we can kind of capture both the short and the long timescales. Another kind of challenge is trip context. Basically, how do we account for the fact that match probabilities might depend on the details of the trip? And the way we do this is basically by extending our regular kind of restless bandit model to account for context. And so now we say that we have some kind of context C that's distributed from some distribution. We say hey, now we have some contextual reward, and it really depends on the state, the action, and the context, where the context might say, hey, this trip is occurring from this location to this location. How does that change your reward? Or how does it change your match probabilities? And what we basically do is we say, okay, now we have another expanded state space. Now our state is not just how engaged is each volunteer, but also how engaged is each volunteer and what is kind of current context. And once we expand the state space, we can also basically change the way that match probability is computed so that match probability depends on the actual trip details. So that, for example, we can learn, hey, look, this person matches much more frequently when the trip is downtown versus this person matches much less frequently. And we can learn this data from our partner organization because they give us a large amount of data on basically who completes the trip and kind of volunteer context or volunteer details. Where's the volunteer located, or at least some proxy for that? How many times the volunteer completed a trip before, so on and so forth. And from that, we can learn match probabilities based on the trip context or the trip details. And so that's how we incorporate kind of trip context into our model. The last thing we want to do is actually define engagement in a way that actually reflects the way that volunteers become engaged or disengaged over time. And this is kind of a challenge because actually defining what engagement means in practice is tricky. And so the way we look at this is by looking at previous data, and we see how does volunteer engagement change as we either notify volunteers more or less. We take volunteers at three different kind of types of volunteers, for lack of a better word. Some volunteers have only completed 5 trips, and these are kind of inexperienced volunteers. Some volunteers have completed 25, and they're kind of in the middle. And some volunteers have completed 50, and they're kind of more experienced. And we look at, as we include more and more notifications, how does the level of engagement or the level of kind of re-engagement between weeks change? Here, re-engagement basically means if I complete a trip in 1 week, what is the chance that I complete a trip in the next week based on the kind of number of notifications I receive? And so we look at this, that's right. And we look at this across these kind of 3 different categories. And what we find is that for the volunteers who are least experienced, the ones with 5 trips, it has a small impact, but basically as you increase the number of notifications, people become less and less re-engaged, or they have a lower chance of becoming re-engaged. And this trend is more dominant when you complete 25 trips, or basically, as we kind of increase the number of notifications beyond, say, 10 or in general, once we increase the number of notifications, we find that the re-engagement rates drop. And basically that is because we kind of over-notify these volunteers and they tend to kind of drop out of the system. On the flip side, when people are very experienced, they actually welcome these kind of more number of notifications and they enjoy the fact that, hey, I get more notifications, I have a higher chance of actually completing trips. And so we can use this data on how the number of notifications impacts engagement rates over time to define to define the state. And we define the state as basically saying, in a given week, has the volunteer completed a trip? And how does that change over time based on the number of notifications? And we learned that from kind of existing data. And here we can see that the re-engagement rate really depends on the number of notifications, and we can incorporate this kind of element into the transition matrices themselves. We run this data over the food rescue kind of data set we get from our partners at 412, and we kind of go over some of the trends that we find from there. The first trend we find is that using our kind of linear and Shapley-Whittle policies increases the trip completion rate. Here we represent this with the reward comparing to kind of the greedy approach that they use currently, and we find that we can improve upon that using these kind of 2 policies. And moreover, what we also find is that we can increase the volunteer engagement rate, basically the fraction of volunteers who are engaged over time compared to kind of greedy approaches. What we find is that there's kind of a steady state level that's, say, 5 or 10% higher compared to the greedy approach. But you can see that both kind of approaches, the number of volunteers engaged decreases dramatically because some volunteers will complete 1 trip and then quit. But after that, we can kind of maintain a steady state level of engagement across volunteers that's higher than the kind of amount that greedy increases or includes. Moreover, we try including context then to see, okay, how does trip context impact things? And we see, okay, if we use this kind of context-based policies, then we can actually also improve performance. And the reason being that we're taking into account the specific kind of match probabilities that depend on, this trip came from this location. Let me actually make sure that the match probabilities for this location are tailored to the volunteers so that volunteers who are closer to the location have higher match probability, and so on and so forth. And so I'll go over some quick kind of other applications of this work, some future questions, and kind of a wrap-up conclusion, and then I'll leave the floor open for questions. And so I'll go over 2 other applications that are related or can use similar frameworks to the kind of restless bandit with global reward presented in this work. One of which is known as volunteer emergency dispatch. And basically, it's a very similar framework to this, or very similar kind of situation. In volunteer emergency dispatch, in some situations, what happens is if people need to go to the hospital or people need to get some kind of volunteer or emergency services, because the emergency services are so kind of booked up, sometimes volunteers themselves might actually drive people to the hospital or do things like that. And so the way that people know about this is through notifications. And so when a kind of new trip or new kind of need arises, volunteers are notified about this. And the same kind of issue arises where you want to make sure that volunteers are engaged while also making sure that the kind of trip completion rate is maximized here. In a similar situation, you can think about peer review, where basically we need to notify reviewers about new papers as they arrive. And the question is kind of, okay, which reviewers do we notify for which papers? How do we make sure that reviewers stay in the system? And how do we make sure that the reviewers we select match the papers that we need to match, kind of review for in a good way? And so you can imagine that both of these are very similar scenarios where we have to notify people over time while having some kind of global reward in context or in kind of scenario. Some of the kind of future questions we're looking at here, some of the kind of open questions range from kind of theory to practice. On the practical side, we're looking at, can we actually deploy this tool for the actual food rescue organization? Can they actually use this in practice? And also, how can we ensure fairness across regions? Basically, how do we make sure that using this algorithm doesn't lead to, say, downtown getting all the food picked up, while more rural areas not getting any food picked up? And the final thing we look at is basically saying, oh, what if the reward parameters are unknown, or maybe the kind of exact match probabilities are unknown? How do we learn this over time in kind of a bandit setting? And what does that actually imply? To kind of recap our problem, basically what we're trying to look at is seeing how can you notify volunteers in this kind of food rescue setting using global rewards? And we do this using restless bandits with the kind of global reward, and we show that we can linearize this global reward as kind of locally linear rewards using Shapley values. And this allows us to improve performance compared to baselines, basically by combining standard restless bandits with this kind of linearization technique. We can further improve upon this by making kind of linear approximations by basically using adaptivity through search techniques like iterative linear whittle and Monte-Carlo Tree Search. And this allows us to improve performance, especially when the reward itself is highly nonlinear. And then we apply this to a food rescue data set, and we show that we can improve both the trip completion rate and also the level of volunteer engagement using our algorithms. And so that's essentially what we looked at through this work. And then we discussed some follow-up work, basically saying, how can we actually deploy this in practice? And so that's kind of the next steps we're looking into. Thank you.
Thanks. This is a great talk. I had some questions, but in the meantime, if anyone else has any questions, feel free to ask them. I can get started. Can you explain more on the context with the food rescue app? Like how do you model the context?
Yeah, let me see if I can go back to that slide. This one. Okay, so basically the way we model context is we say, for a given trip, we have some kind of context vector. And what that context vector contains is information on the trip. And also for each kind of volunteer, we have like a separate kind of vector of, oh, what is a volunteer's information? So trip information or kind of overall global information is something like, where is the trip located? What time of day is it? Things like that. And then for each volunteer, we also have like, oh, what is the volunteer's location? What is the distance from them to the donor, distance to the recipient, et cetera, et cetera. Using this, we can compute kind of, if you recall the match probability P, we can compute P or PI values for each kind of volunteer individually in the current time step using this context. And so we can say, hey, look, volunteer 1 has a 1% chance for this particular rescue. Volunteer 2 has a 5% chance, so on and so forth. And so we can use this to basically get the reward in the current time step. And because we know the kind of distribution of context overall, we also have a sense for what is the kind of expected reward in future time steps as kind of new trips arise in the future. And so we kind of combine these and we basically change our model so that the state space is now not just the state of the volunteers, but the state of the volunteers and the kind of context itself. And so given the state, we can compute all the match probabilities and we have a sense for, oh, how does the state evolve? How do the volunteers evolve? And what is the distribution over my new context? And so we have this kind of augmented restless bandit problem, and we can solve this. We can basically apply our new old techniques to this kind of augmented state space, and allows us to account for the kind of evolving context over time. Does that make sense?
Yep, thanks.
Any other questions?
I think we have one in the chat.
Yeah, let me see. What is the paper name? That's a very good question. The paper is titled Global Rewards and Restless Multi-Armed Bandits. I think it's the same title. And the QR code of the paper is down at the kind of bottom left and bottom right. So if you guys want to take a picture or just kind of Google this, it should be available.
Were you able to implement this practically? Was there any challenges, or if you have, or if you haven't yet, what do you think would be the next step?
I think implementing it is the next step. I think getting anything implemented is always difficult. I think for one, I think the people at the food rescue are kind of, I don't know if protective is the right word, but I don't think they generally want us kind of touching their matching code without kind of thorough evaluation. And even after that, I think, like, for example, explaining like a restless bandit to them is tricky because they're not necessarily technical people. And so in practice, we'd want kind of a much more simplified version of our matching process or a kind of notification process that still accounts for engagement, but kind of boils it down to kind of the essentials that still work well, but might not be as kind of technically sophisticated, so that it's easier to implement, easier to explain, and kind of easier to actually use in practice.
Sounds good. Thanks.
Mm-hmm.
Any other questions?
Oh, yeah.
So yeah, thanks for the great talk. It's been really interesting to see what you're doing. I guess like my contribution sort of is like at the end of the project, you had like some open questions, right? And
Yeah.
then yeah, so I think like one thing I've like learned about fairness recently is like people just like one way people go about fairness is like to check out like regardless of the, so if you have a cohort of, let's say you have a cohort of volunteers, like regardless of, and they are across different groups, ensuring that you have equal sort of like prediction across all those groups, or there's some kind of like there's some bound on variance and just like expectation. Just ensuring that, let's say if your algorithm is accurate 60% of the time for this group, hopefully across all the different groups, you should ensure that it has like, let's say, a similar range. So that's one way I've seen people approach fairness. And I think like Jasmine and the presenter from last week also had some other interesting way about measuring fairness in terms of distance and like how much how much each agent has to contribute in general and like distance. So I think it depends on like how you want to frame the fairness part of it, but I think definitely there are some things out there either from an algorithmic fairness principle or just like based on a particular metric that would like, because your work is very application driven. So like what does fairness mean with respect to like food rescue, right? Is it like regardless of the region, there is like a similar range of frequency of notification, or like, so I think it's very like there'll be certain metrics from the real life setting that you would want to optimize. Say, okay, this is what fairness would look like in the setup.
I definitely agree with that. This is actually, so the open question on fairness, we actually tackled, we should hopefully release a preprint sometime in the next week or two. But essentially the version of fairness we're looking into is inspired by our conversations with people at 412. And one of the concerns they had when kind of with previous algorithms and previous things is that a lot of the time it tends to lead to really high pickup rates in downtown, or kind of the equivalent of downtown in Pittsburgh. But in kind of more rural areas, there's much lower pickup rates, and food tends to kind of go bad, or food tends to kind of not get to the donors as much or recipients as much. And so inspired by this, what we're looking into is, or re-looking to that is basically saying, how do we make sure that we equalize or ensure that each kind of region has a minimum pickup rate? And we do this by basically changing the budget. We have like a dynamic budget so that places in more kind of rural regions, we kind of send out more notifications, and those in kind of more downtown regions, we send out less notifications. And this is because the kind of voluntary imbalance and things like that. And we can basically show that doing so allows us to achieve kind of utility and fairness, or we can show like kind of a trade-off curve between the two. But I agree that there's other kind of notions of fairness at play, like, oh, is there fairness in notification across groups and whatnot? And I think our work, at least so far, the things you're looking to fairness are kind of just a starting point into that.
Yeah. Thank you.
Jasmine?
Yeah, this promises question was very connecting my work, sort of like struck in me that I work on multi-agent reinforcement learning, but fairness in terms of task allocation using like fairness metrics. So in my problem, I usually use navigation-based metrics like distance or time traveled, or like how to distribute the loads equally. And we just picked a fairness metric, like say distance traveled should be equalized amongst all people, so that we don't like ask someone really close by to like just walk maybe 2 blocks and tell someone to like go across the city to pick up their stuff. So that was something, some of the fairness metrics that we looked at when we were doing the fairness for transportation applications.
That's really cool. I feel like that's definitely very relevant. I feel like we could definitely probably use some variant of that in this kind of or framework or different this kind of scenario to ensure some kind of fairness between volunteers or between regions.
I think we have a few more minutes, but if anyone else has any other questions.
No,
If not,
that's
okay,
yeah.
sorry.
I just had a thought, and I wanted to just like pick anyone's brain here about it. So in general, like, what is one reason that we're not framing this problem as a multi-agent, let's say multi-agent reinforcement learning problem?
So
Is it like
huh?
no, you can go.
Oh, sorry. I was going to say we tried to actually try to do that. We tried to just use like multi-agent reinforcement learning techniques. It just did not work that well. And the reason being that this is like in general, this is a much more structured problem because we know the transitions and each arm has independent transitions. And so this kind of structure allows us to kind of more efficiently both give guarantees and find kind of more efficient policies in practice. But when we tried like reinforcement learning based policies, it didn't work as well. At least that's what we found. But maybe there's some kind of variant of some RL policy that actually does well.
Because like what came to my mind, like when David had asked the question about like, oh, how about having like some kind of way to estimate the value of across each arm, like get the expected reward across each arm. It's like there are some multi-agent reinforcement learning algorithms, for example, like COMA, where they try to like solve the problem of credit assignment. It's not like exactly the same thing, but kind of like what you're saying, like trying to figure out if I remove this, let's say I have a group of 3 agents, if I remove this agent, then what happens to the reward? Then that way I kind of think about the contribution of that agent I removed and things like that. So that was one of the reasons I was just like, oh, it seems like there might be some moral algorithms that kind of like capture some of the things you care about, but then it's very interesting to see your approach as well.
Yeah, I think it would have been nice if we could just use a moral algorithm here, but I think at least from our experience, it just did not work for, I think, just complexity reasons. And so we were like, let's try another way that's kind of more theoretical or principled.
Mm-hmm. And then the other question I had, like I noticed like you were using a lot of like, you had some graphs that would have like 4 arms versus 10 arms. Mm-hmm. Like, is there a reason for like choosing a specific number of arms?
Yeah, so 10 we chose because 10 is we chose 10 and 4 in this particular kind of talk. We have 100 and 1,000 in the actual paper, but 4 is chosen for the particular reason that you can actually compute the optimum policy up to 5 or 6, I forget, 4, 5 or 6 arms. And you can basically brute force up to that. We can go, and it's a slow algorithm, but you can basically find the optimal policy, and that allows us to kind of give like a ground truth, like, oh, no policy can do better than this. And so that's why we wanted like a small number of arms and also something that's slightly larger as well.
Okay, so can you remind me again what the justification was for choosing 10?
10 is just, we just wanted some way to see what happens as you scale the number of arms. we also run, like in the actual paper, we also do this with 25, 100, and 1,000 or something like that. I think just for the purpose of the talk, just because it's easier to present with 4 and 10, we just present it with 4 and 10.
Yeah, sure. Thanks. And then, okay, I'm gonna ask this question and shut off. Like, is this like typically what you refer to as a multi-objective reinforcement learning problem? Because I think I've heard about that, and I was thinking that meant you were optimizing maybe different reward for were optimizing different rewards or something at the same time. But like, how is this particular setup you've described, let's say, different from a multi-objective RO setup?
That's a good point. I wouldn't say I'm like entirely familiar with the multi-objective literature. And so I can't really say how we differ. I can say in our scenario that we do have multiple objectives and we do try to kind of maximize the sum of the two. But we only have 2 objectives in this scenario. So I don't know if it's necessarily multi-objective as much as just 2 objective. But also I'm not that familiar with the multi-objective literature.
Thank you so much. Yeah.